All right, and welcome back. So this is now the second of the videos associated to section 5.1 on sequences. I'm going to walk us through three sort of prototypical homework problems. They're actually pulled from your book. They do not appear on the homework, although it's a bit of a shame because they would have been great. Give me just a second. There we go. So we're going to pick these three problems because we're going to do a nice job of indicating some of the things that we talked about in the first video and that you read about. So we're going to solve number 10, number 30, and number 48 from the chapter. I think these are challenging problems, but by no means undoable. Just to highlight again a variety of questions that you should be expected to answer. So number 10 gives us a sequence: 0, 3, 8, 15, 24, 35, 48, 63, 80, 99. And it asks to find an explicit form for these. And I like this question because it highlights exactly how challenging that it can be to do this. You look at those numbers and probably at first glance, unless you really are good at pattern recognition, you're probably not real sure how to start this. So one nice strategy, and actually a way to write down a completely correct answer that isn't the one that your book is expecting, is, you ask yourself, is it an arithmetic sequence? So if it were an arithmetic sequence, the difference of each two consecutive terms would be the same. But that's clearly not the case because, of course, this difference is 3, this difference is 5, this difference is 7, this difference is 9. Hey, wait a minute, it's not an arithmetic sequence, but I'm starting to notice a pattern here. Let's just keep going. 11, 13, 15, 17, oops, terrible. 19. I might have also thought to check whether it was a geometric sequence, but of course you'll see immediately that it is not. In particular, 3 divided by 0 would be a kind of problematic ratio to take, but 15/8 is not the same as 8/3. So I do see a pattern here. In fact, there's some good question about whether there would be a way to sort of set things up by sort of augmenting an arithmetic sequence somehow. Certainly there is a recursive definition that is available here, by the way. But nonetheless, it turns out there's a slightly easier trick. And the book actually does give it to you as a hint. Again, I like this problem because in isolation, it highlights how difficult this process can be. Well, what the book says is add 1 to each term. So let's do that and let's see what happens. And possibly by now, you are starting to recognize that a very specific sequence of numbers is occurring. What is that going on with the choral numbers written above the line? Well, they are precisely the perfect squares. In fact, they're n squared if n represents their place in the sequence, right? 1 squared is 1, 2 squared is 2, 3 squared is 9, 4 squared is 16, et cetera, et cetera. So our original sequence then can be described as the nth location in the sequence is obtained by squaring n and subtracting 1. And so this then will be the answer that the book is looking for. Again, this problem will not make your homework, but it would have been a great one. But I like it because, again, it highlights that this isn't an obvious thing by any means whatsoever. And even after you're doing this for a long time, you look at it and you start to say, I don't really know exactly how to do this. Again, looking at these differences and noticing that there's a pattern going on here, you might not have noticed that, by the way, about the different squares. The difference of 2 squares is given by sort of the next odd number in the list that is actually a consequence, for what it's worth, of this expression, because what do we get? We get 2n plus 1. So this is why this expression, this thing, is why these odd numbers are all occurring. It's because 2n plus 1 is just indexing over the odd numbers. But again, so here we go. We have written an explicit, we've given a stated sequence now in an explicit form. And so this is what the problem was asking us to do. This is something we're going to do quite a bit throughout the homework and throughout some of the outcomes related questions. All right, number 30 is giving us an explicit sequence. It's kind of a weird one. I love it. N to the 1 over n. And it's asking us to figure out how this limit behaves as n gets large. This is tricky because it's a little weird, right? If you think about what's actually going on, you are taking larger and larger numbers, so they would be going off to infinity, but then you're taking smaller and smaller roots of them. And so it's difficult, I think, for people to sort of estimate how that trade-off is going to work, right? What is the millionth root of a million? Well, a million is a large number, but the millionth root of something is extremely small. This is also just a nice opportunity to highlight where something like logarithmic, essentially logarithmic differentiation, but it's really, I guess in this case, logarithmic solving of limits is such a nice way to understand things. So I am going for the moment to assume that this limit exists, but I don't know what it is. I'm going to call it L. So I'm going to say L is the limit as n goes to infinity of n to the 1 over n. What I'm now going to do, I'll give myself some space here. What I'm now going to do is a very nice little trick, which is that since log is a continuous function, I can take log of both sides. So it's a bit of a trick. This is the same trick that's used, for instance, in logarithmic differentiation. But more importantly, because log is continuous, it will actually commute with the limit. So this is a nice little trick. So log commutes with the limit. And you may ask, why did I do this? Why did I want to take the log? Well, because what does log do so brilliantly? It turns exponents into coefficients. And so in particular, this last expression is just the limit as n goes to infinity of 1 over n, ln of n. And again, that's made our problem much, much simpler. And same trick, again, for those of you who are familiar with logarithmic differentiation, this is just using the same principle, but basically logarithmic evaluation of limits. And the key to this, and again, this is in our opinion a 10A thing, but it's worth jogging your memory, is that this equality is because log commutes with limits because it is a continuous function. So here we have arrived at this expression. I want to know how this limit behaves. Well, frankly, for that purpose, I can just ask about the similar function, x goes to infinity of ln x over x, right? This has now turned my sequence that I was interested in into a new sequence, which can easily be written as a function. And now I want to understand how this sequence behaves. As x goes to infinity, of course, both of these terms are going to go off to infinity. And so that kicks in. I know how to solve something like that. It means that I need to turn to our old friend L'Hopital's. And by L'Hopital's, this is the same limit. And I'm going to take the derivative of the top and bottom separately. So 1 over x over 1. As x goes to infinity, that's going to go to 0. So again, just to be clear here, because I chose some hard ones. So if this is not obvious to you, that's okay. That's why we're doing this. So initially I started with this L and I wanted to know the limit of this sequence. This sequence you can't really just set up as x to the 1 over x because we haven't really made sense of like, you know, what a power looks like if it's not an integer. But I say, okay, if this sequence has a limit, I'm going to suppose it does for the moment. Let's take log. So we take log and we can rewrite this expression. Well, first off, log being continuous commutes with the limit. And then the exponent here can pop out as a power. So we arrive at this expression. By taking log, we've now arrived at a completely different sequence that we want to understand the end behavior of. But that sequence, it is very easy to write down in the form of a function that agrees with it. So again, we had that theorem from the previous video that if you could write down some function f of x for which f of n was a sub n, and the f of x was well behaved, then the a sub n was well behaved. I think I actually even have it from the previous notes. So here. So that's what this theorem, just to jog your memory, that's what this theorem was saying. If you can write down the a sub n's as the explicit values of some function, and the function is well behaved, then the sequence is well behaved. And so that's what we're doing here. So now zipping back forward, hold on one second, it seems to have, nope, okay, there we go, a little bit of a delay. So I want to now understand something about this sequence. I can write it down in explicit form as this function. And this function, if it's well behaved, will tell me how the sequence also behaves. But the key about a function is that I can use L'Hopital's. In particular, the key about a function is that I can take derivatives. Right? I can understand how the function is much, much easier for me to work with functions than it is for me to work with sequences. Because when I'm dealing with functions, I have all these tools that we've developed in 10A, derivatives, L'Hopital's, you know, understanding all sorts of things, integrals later on. And I don't have those for sequences, but this theorem lets me get a little bit of that back. So in particular, I see that both the top and the bottom go to infinity. That's a key time to use L'Hopital's. So I take the derivative of the top and bottom separately. Again, you can't really take the derivative of a sequence of limits because slopes of secant lines don't make sense. The graphs are very discrete. They only have a dot, every integer value. So they don't really amend themselves or lend themselves to calculus-based techniques, but functions do. And in particular, I see that this function goes to 0. Now remember, by the theorem that we showed you just a minute ago, that means this sequence also goes to 0. And this sequence was the log of the thing I was interested in. So I have arrived at the conclusion that ln of L equals 0. And by exponentiating both sides, I get that L is e to the 0, which is 1. So in fact, rather, I think non-trivially, the limit of n to the 1 over n. So what happens is you take the billionth root of a billion, or the trillionth root of a trillion, and the limit is actually just 1. Again, pretty cool problem, and a nice survey of methods that you may have forgotten about. All right, what about something like this? This one's actually a little easier, frankly, than the number 30 was. So this is number 48, and it's actually given us the formula in explicit form this time, or the sequence in explicit form, which is kind of them. It's log of n squared over log 2n. And I'm going to do this two ways. So the first way, of course, is that it is fairly easy to write f of x as the function ln of x squared over ln of 2x. And you will see immediately that a sub n is given by evaluating f at the value n, at the integer n. So by our theorem, if the limit, this is the theorem we used just before, but I gave myself more space on this one. If the limit of this function equals L, then the limit of this sequence is also L. So I'm reduced to trying to understand how this works. So I look at this limit. This is the limit as x goes to infinity, ln of x squared over ln of 2x. Notice again, just like before, both terms individually are going to go off to plus or minus infinity. And so this is a perfect time for me to use L'Hopital's. When I do that, by the way, I know that most students don't do this. I tend to just write a little LH above the equality because it tells the grader immediately what I'm using. So actually, this is exactly how I write it on an assessment. So I indicate that the terms are going off to infinity, and I indicate that I've recognized that I can use L'Hopital's as a result. I think this is just a really clean, concise way to explain to the grader exactly what you're doing. The value of that is that then it's very clear that you understand what's going on and that you've done it correctly, easier to give you points. So I go ahead and take the derivative. The derivative of the top, I would still get the limit, and let me be careful with my limits because this is, of course, the example video. So we still need to understand how the limits work, and this gives me 2x over x squared over 2 over 2x. The significant amount of cancellation that's about to happen in the individual and in the numerator and denominator separately already told me that I probably could have simplified my answer before I even got this far, but you'll notice that this is the same. Again, before I even worry about the whole, a fraction of fractions is the whatever, multiply by the reciprocal, I'm going to notice that already the top could just be written as 2 over x, and the bottom could be written as 1 over x. And so this then tells me that this is going to tend to 2. Because, of course, now I simplify. So now the 1 over x's cancel. So here just a minute ago, this canceled with this canceled with this, and now the x cancels with the x. And in fact, this is just constantly 2. So by L'Hopital's, our function tended to 2, and therefore by our theorem, our sequence will also tend to 2. So we arrive at the conclusion, the correct conclusion, that, say therefore, the limit as n goes to infinity of ln of n squared over ln of 2n equals 2. And this would be the answer that we're looking for. I want to point out, however, that massive amount of cancellation sort of gives rise to another way to do the problem, which is the following. So let's say alternatively, this is not adding on, this is doing the problem a different way. So alternatively, that's a very bright color. Alternatively, let's look at this limit. Before we do anything, let's just look at the an term. So it's ln of n squared over ln of 2n. My dog has just joined me. Oh. And notice that that's the same thing as 2 ln n over ln of n plus ln of 2. So all I've done here is used two properties of logs. One is that the exponent, of course, like we just used a minute ago, can come down as a power, so I get a 2 out front. And the other is that the log of the product is the sum of the logs. Now, if you think about it, right, it is, as n gets big, log of n is going to get very, very big. It goes off to infinity, although it gets there slowly, but it goes off to infinity. And what that means is the denominator, the log of 2, basically doesn't matter anymore. When n is large, the log of 2 is not really changing anything. So this term, and you can actually make this concrete with the squeeze theorem, which is what I'm going to do in a second, this expression basically looks like 2 log of n over log of n. Notice I've used the typical math, squiggly braces, squiggly equality, which right now means I'm hand waving a little, but again, we're going to do this a second with the limit law. Sorry, with the squeeze theorem. But essentially that denominator doesn't really matter, right? The log 2 in the denominator, it doesn't matter. It's saying I have this really, really big number plus log 2. Well, as far as the fraction is concerned, it's almost as though you didn't have to add the log 2. And so what you see is that this expression is approximately just 2 ln over log n, and those cancel, and we get the 2 that we know to be a correct answer from above. So let's make this rationale rigorous with the squeeze theorem. Okay, I actually just spent a little time trying to see if there is indeed an easy example of the squeeze theorem sitting, like floating around here in the ether. And the answer is I don't actually think there is, but nonetheless, I do want to highlight the methodology. So I'm going to use it, but I admit that this is a little bit contrived because we already knew what the answer should be. But I want to show you how the squeeze theorem could apply in this case if you felt like working hard enough to apply it, which I'm not actually sure that you should. So let's look at our sequence. Our sequence, again, if I write it like this, is 2 ln over ln n, log of n, plus log of 2. And I notice immediately that, of course, as we just observed a second ago, in order to make a fraction bigger, I can either make the numerator bigger or I can make the denominator smaller. So this expression is indeed smaller than if I just take away the ln of 2 from the denominator. Okay, a lot of interruptions tonight. All right, so the point here, again, even though this was 2 seconds ago for you and you're like, why is he recapping? Well, because it was quite a long time ago for me and I need to remind myself of where we are. I'm going to use the squeeze theorem, even though I'm going to tell you up front, or sort of retrospectively, that it's not the right way to do this problem. But nonetheless, I want to highlight the method. So here was the original sequence that we needed to understand. In order to use the squeeze theorem, I need to find something which is bigger than it and something which is smaller than it, and for which both of them go to the same value. That's how the squeeze theorem works. So you find something smaller, you find something bigger, and you prove that they both converge. The point of the squeeze theorem is then that this limit has no choice but to go to the same thing, hence the name. So here I have trivially made my expression bigger by making the by making the denominator smaller. Making the denominator smaller will make a fraction bigger. So I've simply cut out the log 2, and you'll notice, of course, that these just cancel, and this is just 2. So our goal, of course, and we know because we already did it, is to show that this limit here, this series here, sorry, this sequence rather, apologies, converges to 2. And notice that 2, of course, will go to 2. So now all we need to do is find something below that also goes to 2. And then we're good. That's how the squeeze theorem works. The problem is that it's really not that obvious how to find something that's smaller that trivially goes to 2. But I'm going to do it in the following way. I'm going to cleverly rewrite this. This expression can be rewritten, if you think about it, as 2 ln n plus ln 2 over log n plus ln 2. Notice I've added, so I'm not done yet. This is not a rewriting. I've added a 2 ln 2, which wasn't there originally. So I need to subtract 2 ln 2 and over the same ln n plus ln 2. So this, all I've done here is cleverly added and subtracted the same term. So it didn't actually change anything. The key, however, is that this expression here is bigger. Remember, I can always make, so this is a little tricky, I can always make a fraction bigger by making the denominator smaller, but because, so this is the term I'm going to look at. Notice this just cancels. This is just 2. This is the term I'm going to look at. And if I make this expression here bigger, because it's being subtracted, I will actually make the whole thing smaller. So my claim is, and again, we're going to talk about this again in a second, that this, oops, sorry, I don't want the 2 here, I want n. So my claim is that this expression here is smaller than what I started with. Strictly smaller as it happens. So all I did, and again, no one would do this unless you already knew the answer. So it's a silly example to use the squeeze theorem on, but since I already started it, we might as well finish it. I wanted to prove that this converges to 2. I bounded it above trivially by something which is identically 2. It doesn't even depend on n once I do some simple cancellation. So obviously that's going to go to 2. So the goal is to bound it by bound this expression by something from below, which will also tend to 2. To that end, I just cleverly rewrote the top in a way that didn't change anything. Cleverly multiplying by 1 and cleverly adding 0 is basically what mathematicians sit around doing. And then I went ahead and separated this into 2 fractions. I can make this expression bigger by, oops, wrong term. I can make this expression bigger by canceling out some of the denominator, by making the denominator smaller. And because this is being subtracted, that will make I'm now subtracting a larger number, which means that I get a smaller expression. There's a whole lot of inequalities going on here. But the long story short is that this expression here is smaller than the one I started with. And now I pass to a limit. So of course, by taking the limit of everything, the constant function 2 is obviously just going to go to 2. It doesn't even depend on n whatsoever. Here, of course, the 2 will stay 2. And notice that this expression, my denominator is getting big, my numerator is not. So this is obviously, this individual piece here is going to go to 0. So by the limit laws that we still have, I get 2 minus 0. So this also goes to 2. And then ta-da, by the squeeze theorem, this expression has nowhere but to go to 2 as well, because it's been bounded above and below by 2 expressions that are literally squeezing together to 2. Then the squeeze theorem says this also will go to 2. And that's how you use the squeeze theorem. Again, in this particular case, not the easiest way to do the problem, but at least now you have some understanding and have seen an example of it. And generally you can do things with the squeeze theorem. It's just a question of how clever are you with your inequalities. So again, it's a good method to have in your back pocket, even if maybe none of the questions that we're going to ask you necessarily rely on it. If you can use it correctly, you're all set. All right, best of luck.